So let's get into different types of mixtures. So we have homogeneous mixtures and heterogeneous mixtures, and I'll explain the two. Homogeneous mixtures have a uniform composition. The particles in the mixture, they're evenly spread out, as you can see in the picture. And an example would be salt water. You can't see the individual particles or ingredients in a homogeneous mixture, even with a microscope. So if you had a microscope, you would not see this. This is just a model to kind of explain what it looks like in theory. But if you had a microscope and you looked at salt water, you would not see the individual salt particles. You would not see the individual water molecules. And also, homogeneous mixtures don't have to be liquid. They can also be solid. A solid homogeneous mixture is called an alloy, and alloys usually have at least one metal ingredient. Let me explain what I mean. Say we have carbon excuse me, let me back up a bit. Say we had iron. If I had iron and I melted it down, so this is a picture of a melting iron, and then if I were to mix in carbon, when that mixture cooled, and I could shape it however I wanted to, I would get steel. And steel is an alloy. It is a homogeneous mixture of iron and carbon. And the great thing about alloys is, since mixtures have the average properties of their ingredients, steel is going to be stronger than pure iron. So a steel bar is not going to bend like a pure iron bar will, because carbon doesn't bend. Iron bends, carbon doesn't bend. When you mix them together, you get steel, which is as strong as iron, but it doesn't bend like carbon. And that is what an alloy is. Now, a homogeneous mixture of two solid substances. Now, heterogeneous mixtures, they have a non-uniform composition. What that means is that the particles in the mixture are not evenly spread out. And you can see in this picture, all of these particles are settled to the bottom while the rest of these are on top. So they're kind of separated from each other. Non-uniform composition. That's as opposed to this over here, homogeneous mixtures, where everything is kind of evenly spread out. Heterogeneous mixture, everything is not evenly spread out. This is a good example, sand and water. Now, in a heterogeneous mixture, you can see the individual particles. So I can see the ingredients that make up sand water. I can see the sand on the bottom. I can see the water on top. In a homogeneous mixture, I can't see what these individual particles are. Now, for some mixtures like milk, you will need a microscope to see the individual particles. That heterogeneous mixtures are also called suspensions. Now, you have suspensions and you have colloidal suspensions. These are two different types of heterogeneous mixtures. Now, in a suspension, the particles will eventually settle to the bottom if the mixture is left standing for a long enough time. So this sand water that we saw here, that would be a suspension, because it might have been mixed up at one point, but it's been sat down and all of the sand sank to the bottom. So in a suspension, the particles are eventually going to go to the bottom of the mixture. And there's my sand water example. Now, in a colloidal suspension, the particles will not settle to the bottom on their own, no matter how long the mixture is left standing. And so in this example, I have a glass of milk. Milk is a colloidal suspension. Now, it looks like a homogeneous mixture because to the naked eye, you can't see the individual particles, right? But if you were to look at milk under a microscope, it will look like that. And you actually can see the individual fat globules and other ingredients that make up milk. So yes, milk is a homogeneous. Yes, milk is a heterogeneous mixture. It is a colloidal suspension because you need a microscope to see the individual particles. Now remember, with a homogeneous mixture, even if you had a microscope, you would not be able to see the individual particles. So it's important to know that distinction. Now, I'm going to talk about solutions. Solutions, we're going to be able to describe the properties of solutions and explain how they are formed. So, again, we review the types of mixtures, homogeneous mixtures and heterogeneous mixtures. A solution is a homogeneous mixture. Okay, a solution is a homogeneous mixture. That's what it is. Solutions are homogeneous mixtures. Solutions can be solid. For example, alloys. Solutions can be gaseous, like in air. Air is a gaseous solution. But usually, when we talk about solutions, it is a liquid homogeneous mixture. That's what we usually are talking about when we talk about solutions. Now, solutions are composed of a solvent, which is the main ingredient, the primary ingredient in a solution, and also the solute, the other ingredients in a solution. So you put a solvent plus the solute, you get a solution. So if we had water as the main ingredient, and water is the main ingredient in many solutions, water is the solvent. And then if we put salt in that water, salt is an additional ingredient that we add in, so salt is the solute. And that gives us salt water, which is our solution. Another example. Let's say we had nitrogen gas as the main ingredient, the primary ingredient. That would be the solvent. And then say we mixed in a little bit of oxygen, little argon gas, and a little carbon dioxide. They would be the solutes. Now, can you recognize what solution these ingredients make? They make air. So air is actually a solution, a gaseous solution of nitrogen, oxygen, argon, and carbon dioxide, and trace amounts of other gases. Nitrogen is the solvent because it's the main ingredient, and air is actually around 70% nitrogen. Then the solutes are the other gases. Those are the other ingredients. So yes, solutions can be gaseous. Alright, now my salt water is an aqueous solution. An aqueous solution is a solution in which water is the solvent, the main ingredient. Aqueous solutions, they get their own, they get special attention because they're so important because water is the solvent in so many different mixtures and so many different solutions that aqueous solutions get their own category. Now let's talk a bit about solubility and what does it mean for something to dissolve in something else. The solute dissolves into the solvent to create a solution, and this occurs because of the random motion of the molecules of the substances. If one substance can dissolve in another substance, then it is soluble in that substance. Salt is soluble in water because we know that salt can dissolve in water. So salt is soluble. If a substance cannot dissolve in another substance, then it is insoluble in that substance. So let's look at this example. This is copper in hydrochloric acid. Now, a lot of metals will dissolve in hydrochloric acid. Copper will not. Therefore, we say that copper is insoluble in hydrochloric acid. Acid at room temperature anyway. Alright, now this is something new. Polar substances only dissolve in other polar substances, and nonpolar substances only dissolve in other nonpolar substances. So let's see what polar means so we can understand what that statement means. Water is polar. What does it mean that water is polar? Well, let's look at a water molecule. That's my water molecule. Oxygen and two hydrogens chemically bonded together. The hydrogens have a positive charge, so this end of the water molecule has a positive partial charge. So positive on this end, but down here near the oxygen, there is a negative charge. So down in the oxygen, we have a negative partial charge. So the molecule charges kind of point in that direction, with positive pointing in this direction and negatives pointing in the other direction. And that's what I mean when I say that the water molecule is polar. You know, it's polar because it's pointing, it points in a certain direction because one end is positive and the other end is negative. So, water is polar, and polar substances only dissolve in other polar substances. So, water is going to dissolve alcohol. So, if I were to take alcohol and put it in water, it will dissolve and create a solution. Now, nonpolar molecules, they don't have that charge. They don't have those partial charges. Oil is an example of a nonpolar molecule. It's made of nonpolar molecules. Now, oil will dissolve paint thinner because paint thinner is also nonpolar. So polar dissolves polar, nonpolar dissolves nonpolar. And a quick, easy way to remember that is the saying, like dissolves like. Polar dissolves polar, nonpolar dissolves nonpolar. Now, when two liquids are able to dissolve each other, they are said to be miscible. They're said to be miscible. So, polar water and nonpolar oil, they will not dissolve each other. That does not create a solution. It's actually going to create a suspension. So, when two liquids do not dissolve each other, they are said to be immiscible. So, water and oil are immiscible. They do not dissolve each other. Now, the thing with solubility, it can be affected by different factors. So here I have a glass of water, and someone threw a sugar cube in there. If you take a glass of water and pour in sugar from a spoon, granulated sugar, the picture on the right is going to dissolve faster. The sugar is going to dissolve faster here than it will here. And the reason why is because the sugar here has a higher surface area. See, over on the left-hand picture, the cube, there are only 1, 2, 3, and 3 on the other side. There are only 6 faces of the cube of sugar touching the water. It's only going to dissolve but so fast. But when you have a bunch of tiny little sugar particles, you have a much more sugar touching much more water. So with that greater surface area, solubility will increase. Now, if you want to increase solubility even more, what you do is you raise the temperature. So here I have water boiling on the stove and I'm pouring sugar in. It's going to dissolve even faster because solubility increases with greater temperature. See, temperature is a measure of how fast the molecules are moving. So at a higher temperature, the molecules are going to be moving around a lot faster and the sugar is going to dissolve a lot faster.